Okay. Well, thank you all for joining us today again for another ARC seminar. Today we have Ryan Bennink from the Oak Ridge National Laboratory. Ryan leads the Quantum Computational Science Group at Oak Ridge National Laboratory. And for the past decade, his research interests have focused on the developing of quantum computational methods and on modeling and simulation of noisy quantum computation. Prior to that, Ryan developed state-of-the-art entangled photonic sources for quantum information science applications. Ryan received his PhD in optics from the University of Rochester and undergraduate degrees in physics and mathematics. He studied abroad as a Marshall Scholar. He was a Sproul Fellow at the University of Rochester and joined ORNL as a Wigner Fellow in 2004. Today, Ryan joins us to speak about his work on quantifying the expressiveness of parameterized quantum circuits using a new interpretation of frame potentials. So, Ryan, please take it away.
All right. Thanks, Greg. And thanks for inviting me to give this talk. This is something that's been kind of brewing in the background of my research for a little while, and but it's kind of finally coming to fruition. So I'm pleased to be able to talk about it. This work kind of actually started a couple of years ago. We were starting to look at just trying to understand the expressiveness of different parameterized quantum circuits, these ansatz, very popular in VQE and other kind of variational applications. And I was plotting these graphs, and one of my staff said, well, wait, what's that quantity mean? And I realized I had no good answer for it. And so that kind of, that one innocent question set me off on a whole research direction. So that's what I'm going to talk about today. Variational quantum computing is a very important approach to computing in the current era. It's a very hardware-friendly approach. So it's you have an ansatz, a variational ansatz that happens to be a quantum circuit with tunable parameters, and you adjust the parameters of the circuit to try and achieve some result, which is the answer to your computation. And this is
Ryan, sorry to interrupt you.
I'm not sharing.
You're not sharing. Yes, I thought maybe you're doing an introduction before, but then
I was, and then I kind of I forgot. When I first was going to do it, it said you're going to steal the other person's screen. Do you want to do this? And I said no.
Okay.
No. All right. Hopefully you can see it now.
Yep.
All right. This is prevalent in optimization, quantum machine learning, and quantum chemistry, things like that. But in all these applications, a key to the success is formulating an appropriate ansatz. And you want your circuit ansatz to be able to prepare any desired state within some target class. On the other hand, you don't want it to be too general or too complex. If it's too complex, you will have a hard time doing it on the hardware. And also, if it's too general, then it'll be difficult to optimize. In my opinion, I think the community does not have the understanding of how to design ansatz, or even just to assess them to the extent that we would like. So kind of a very basic question in my mind has been, how can or how should we quantify the expressiveness of a parameterized quantum circuit? And I think we all have an intuitive notion of what expressiveness means, but how can we formalize that? Just as a quick note, in this work, I'm going to be focusing on the task of state preparation, but I think all the ideas that I'm talking about, you could generalize to circuits that are designed to realize unitaries. So to give a quick overview of the main results first, I'm going to propose a general definition of expressiveness that quantifies the intuitive notions. And something notable about this is that it's not just one number, but it depends on a resolution parameter. And I'll argue why that's kind of valuable. The main technical result is that I connect something called a T-design frame potential to the volume of states that your circuit can approximate to a given accuracy, which is, and I'll explore that. And then I'll conclude by calculating the expressiveness as defined in this way for several quantum circuit ansatz. Okay, just a little bit of background. I'm not the first person to think about expressiveness. Others in recent years have done so. Some work has defined expressiveness in terms of the ability of the circuit to create entanglement. Another approach, perhaps the most common one, has been to relate expressiveness to closeness to something called the quantum state 2 design or quantum unitary 2 design. You know, it's been used for a lot of things, not just quantifying the expressiveness of variational circuits, but it comes up in proving things like complexity classes, like how hard is it to simulate a quantum circuit, information scrambling, how does information get scrambled, and so this comes up in a lot of areas. Another approach, which is related to the quantum 2 design, has been to look at something that doesn't have a name to my knowledge, but I call it the pairwise fidelity distribution. And looking at that, you can sort of compare the distribution to a certain sort of ideal maximally expressive circuit, and that's your way of quantifying expressiveness. And then there's something recently called a covering number, and the idea there is you take the set of states that your circuit can make, and you ask how many patches of a given size in Hilbert space would it take to cover the set of states that you can actually make. And that metric is perhaps the most similar in spirit to the one I'm about to propose, but the technical details are actually more related to these quantum 2 designs and pairwise fidelity measures. Okay, so let's take a step back. What is the problem, and what are we trying to measure? So if you have a parameterized quantum circuit, you're trying to prepare states within some target class. And this, for example, your class might be ground states of the Hubbard model. And so that's your target class shown in pink. And then this is the set of states that your circuit can make, and it may overlap some of your target class. And so the question is, can I make all the states in my target class, or how much of the target class can I actually make with this parameterized circuit? Well, that was a little bit too hard of a problem. So I said, well, let's say that our target class is the whole Hilbert space, in which case the question becomes, what fraction of state space can we reach with some parameterized quantum circuit? Now, the obvious idea would be to say, well, the expressiveness is just the volume of this set that I can make. And it turns out that's actually not a very helpful idea for the following reason. If you have a circuit with m parameters, then the set that you can make is generally going to be some surface that has a dimension at most m. And since the number of parameters is generally less than the dimension of the Hilbert space, right? Hilbert space is big. You have a manifold which is of a lower dimension. And so strictly speaking, the volume of that manifold in this larger space would be 0. So that's not an informative metric. And this would prevent you from comparing the expressiveness of ansatz that have different dimensionality or different numbers of parameters. So how can we get past that? Well, in every application, there's going to be some tolerance to error, right? So if two states are sufficiently close, then they're effectively the same, right? So if you can make some target state to sufficient accuracy, that's good enough. So what I propose is that is to measure expressiveness of a circuit as the measure of states that are that you can approximate to some given accuracy threshold, or to state another way, a set of states that are within a certain distance of the states that you can actually make. And so this is actually a very general definition. You can choose different distance functions for measuring distance. You can there's an underlying notion of a measure on your state space, and then the notation here, phi sub d, that means the set of states that are within a distance delta of the set phi that we can make. And so in this notation, the expressiveness can be simplified as this formula. It's the measure of the set of states within a distance delta of the states we can realize. Okay, that was kind of mathy. As I said, this is very flexible. We can have our distance function be lots of things. It could be infidelity, it could be trace distance, it could be cross entropy, kind of whatever we want in our application. Our state space measure could be a geometric measure, or it could be some sort of prior probability. So that's the flexibility is something that's nice. Another feature of this definition is that it's inherently tied to the thing that you care about, which is your ability to prepare states to a given accuracy. Now, another kind of notable feature of this definition is that it depends on this resolution or error tolerance parameter. It's not just a single number. And, as I said, the motivation for that is in every application, you do have some error tolerance. But it's also important because you can have parameterized circuits that may seem to have the same expressiveness if you're looking at a very coarse resolution, but they may have very different expressiveness once you zoom in and look at fine resolutions. And so this is another knob for you to explore. And in fact, the way that the expressiveness depends on resolution can actually reveal something about the structure of the set of states that your circuit can realize. So let me kind of show some cartoons to kind of explain that. So here I have three sets shown in green, and these are pretend that these are different sets that your circuit can make. And the dashed box is, we'll say that's Hilbert space. And so here I have three sets, one of which has a large extent and a large volume, another one that has a large extent but a small volume, and a third that has a small extent and a small volume. And what we're going to do is we're going to look at what fraction of this set of Hilbert space, this whole box, is within a certain distance of the states that we can make, shown in green. So let's say we start with a very large resolution parameter. So for all three of these sets, if you look at the states within a distance of 8, that includes the entire Hilbert space. So all three of these measures, they have a maximum volume. As we start to decrease our resolution parameter, the set that has a small extent and a small volume, we see it starts to not fill the whole Hilbert space. Whereas the ones that have large extent, if you look at all the states that are within a distance 3, that still covers the whole state space. And as we continue to decrease our resolution parameter, now even the ones with large extent, we start to not fill the whole state space. And so for these three different categories, we get three different looking curves. And there are kind of three notable features. The first is, at what resolution does your volume start to drop off? And that tells you about the extent of your set of states. Then you can look at how rapidly does it start to drop off. That tells you the curvature. That tells you about the dimensionality of your set of states. And then for very small values of delta, where that intersects, that starts to approach the actual volume of your set of states. And so by looking at the shape of this, the resolution dependence, that can tell us about the structure of the set. Okay, so this is maybe a nice idea, but this measure is actually not very practical. If you want to, calculate the measure of states that are within a certain distance of your realizable set, that would require you to, for every state in Hilbert space, to find the closest realizable state and compute its distance. And this is going to be difficult. So this is going to require some generally nonlinear optimization, which is going to be unreliable and costly and difficult. So you might ask, well, is there some other quantity that we can calculate more easily that sort of tells us something similar? We can use it as sort of a proxy for this idealized notion of expressiveness. And there's another question which drove this work, which is, can these integrals that appear in the definition of quantum T designs, which show up a lot, can we somehow relate those to this more idealized notion of expressiveness that we would like to measure? And it turns out the answer to both of these is yes.
Ryan, can I
Yes.
ask a question?
Yeah.
Is there a reason why that nonlinear optimization problem is so difficult or unreliable? I mean, it sort of seems like finding a projection onto capital psi phi, shouldn't be that hard for a given psi, or you have to I don't understand for every. Is it just for each instance that you're trying to consider?
Well, I mean, so it's an optimization problem, right? So you can say I have a circuit and I want to maximize its overlap or its fidelity with a given target state. And that optimization function might be very lumpy, right? It might have lots of, it might be like an eggshell or eggshell carton, right? With lots of peaks and valleys. So I think in general, it's you can find a state that is sort of a local optimum, but I think finding the actual closest state is a challenging problem.
Okay, thanks.
Yeah. Okay, so in this next section, I'm going to talk about something called quantum state T designs and frame potentials. So just a bit of background. Let's say you have some distribution mu over quantum states. And that's called a state T design if the average value of some degree T polynomial, or any degree T polynomial, is the same as averaging that polynomial over all quantum states. So this is the uniform distribution of quantum states. That's called the Haar invariant measure. And so if the distribution over, if your positive distribution gives you the same value as the uniform distribution, then that's called a T design. And you can measure the closeness of a distribution or a measure through these things called frame potentials. These are integrals. So it turns out that these integrals work out to be something that I call the pairwise fidelity, which is you pick two states at random and then compute their fidelity and raise that to the power of t. And then you just integrate over, the expectation value. And so this is called the Tth frame potential. And it turns out this distance, this difference is greater than 0. And the closer it is to 0, the closer your distribution is to the uniform. And so that relates to expressiveness. So how can we relate this to quantum circuits? So let's we'll choose some prior distribution on our circuit parameters, and that's going to induce a measure on the set of realizable states, the states that the circuit can make. And ideally, we want this distribution to be uniform on their set of realizable states and 0 everywhere else. It may not actually be uniform. For example, because the mapping from angles to states in Hilbert space is nonlinear, it might be bunched up. But the more uniform we can make it in Hilbert space, the better it will be. So why do these frame potentials have anything to do with expressiveness? So the argument is this. Sort of intuitively, if we have an expressive circuit, that means it can create a wide diversity of states, which means that if you were to pick two of those states at random, they're more than likely going to be dissimilar to each other, which means they're going to have small fidelity. And so that means the expected fidelity is going to be smaller. And so small expected fidelity raised to some power t, the smaller that is, the more expressive your circuit. And then we compare this to the value that you get for a uniform distribution, because that being able to make all states uniformly in a certain sense corresponds to a maximally expressive circuit. And so people use this difference between these frame potentials for at the degree 2. That's the most common used measure of expressiveness. But this question that my colleague asked me, what does this number mean? it's really hard to know what it means. So one of my main goals when I undertook this was to be able to relate these frame potentials to this kind of volumetric notion of expressiveness that I introduced a few minutes ago. So to make this connection, I'm going to introduce something called a fuzzy volume. So let's say we have a geometric measure on our state space. We'll call that nu, and you can think of that as being the Haar measure, or something else sort of simple. And now let's say we have some other arbitrary measure mu. This could be a probability distribution, or it could be a distribution that represents a set that we can make. And so I'm going to define the fuzzy volume of this distribution mu as this ratio of the square of this density function p divided by the integral of the square. And this density p is just the ratio of our probability measure to our geometric measure. Now, why is this called volume? The reason is that if you make your distribution uniform over some set that has geometric measure v, then this fuzzy volume is actually equal to that geometric measure. And in general, the more spread out your distribution mu is, the larger this fuzzy volume is going to be. And the more concentrated it is, the smaller your fuzzy volume is going to be. So this is a way of assigning a volume to an arbitrary probability measure. Now we're going to, just for convenience, take our geometric measure to have total volume 1, so that this fuzzy volume is between 0 and 1, which means we can think of it as a fraction of state space, or we can think of it as a probability. Okay. The second thing I want to introduce is the concept of blurring. So let's say, suppose we have a kernel function k, and it's going to be some non-negative function that depends on a pair of quantum states, and it's unitarily invariant, meaning if we apply the same unitary to both states, we get the same value. Then you can show that that means that this kernel function depends only on the fidelity of the two states with respect to each other. Given this kernel, we can define convolution in the following way. We can say we have some measure mu, and we convolve it with k, and that's defined by this integral. And you can think of that as blurring out our measure mu. So let's say our measure mu depends on some parameter locally, some parameter phi, and it looks something like this, shown in red. And our kernel k is shown in blue. It's some sort of broader Gaussian type function. When we convolve mu with k, we see we kind of retain the structure of our original distribution mu, but now it's broadened. It's sort of smoothed out or blurred out. And so that's what this integral does. Okay. So in the rest of the talk, I'm going to use the Haar measure, Haar invariant measure as our geometric measure. And when we do this, the measure of any set now becomes the probability that some random state is a member of that set. Okay, so you may see at some places I use the term volume, at other places I'm using the word probability, but with this choice, they're actually equal. So now let's connect this to fuzzy volume. Let's take this density P that I was talking about, and we'll choose that to be the convolution of some prior distribution mu convolved with this kernel k. If we put that into our definition of fuzzy volume, we get an expression like this, which is you have two integrals, one in the numerator, one in the denominator, and they depend on this function j, which is the convolution of k with itself, basically. And if you're to go back and look at the definition of these frame potential, you'd see that the numerator and denominator each have the form of a frame potential where this f to the t has been replaced by this quantity j. So if we were somehow able to design a j such that it equals this fidelity to the t, then that expression, this fuzzy volume, would equal a ratio of frame potentials. Well, can we do that? We can. You can argue, since we know that f is a unitarily invariant positive semi-definite kernel, that implies that there is a kernel k that when you convolve it with itself gives you this fidelity to the t. And actually, it turns out as long as t isn't too small, this kernel function is pretty close to fidelity to the 2t. And I've shown here a plot. The actual fidelity to the t is shown in solid lines, and then this approximation of what you would get if you took the kernel function to be f to the 2t and you convolved it with itself, would you get f to the t? And as you can see, it's not terrible for t equals 2, but as you get to larger t values, it's actually a pretty good approximation. So this is useful to think of, is that this kernel function is approximately equal to the fidelity raised to 2t. So putting this all together, if we choose an appropriate kernel, we find that the ratio of these two frame potentials, one with respect to the hard distribution and one with our arbitrary distribution, that equals a fuzzy volume of this kind of blurred distribution. Okay, and remember, mu is going to be a distribution that represents the set of states that our circuit can realize. So we're starting to get there. We're taking these two frame potentials, and the ratio we're now saying we can think of as some sort of volume, but it's a fuzzy volume. What we'd like to do is to actually relate that to a volume of states that are within some given distance of the set of states that we can realize. And intuitively, there's an argument that we should be able to make that connection. So we have our kernel K, and we convolve that with a set, and we're going to say it has a uniform measure over the set. And so when we do that convolution, right, we have some characteristic radius for our kernel, and when we convolve it with our set, if you look at what is the support of that blurred distribution, it's going to be roughly the set of states that are within some distance delta from the original set. And so we would expect then that this fuzzy volume is going to be approximately equal to the volume of states that are within a certain distance delta, where delta is the characteristic radius of this kernel function. Okay, and so that's the intuition. In the next few slides, I'm going to go through a few arguments that is actually the case. So I won't go through too much detail, but we find that this relation holds exactly in the asymptotic case. And as we let t become very large, our kernel function actually approximates a Gaussian that has a width that is much smaller than 1. And so we're looking at very close distances in Hilbert space. And over such small distances, Hilbert space is approximately Euclidean. Our set of states that we can realize with our parametric circuit is going to look like some flat manifold or flat subspace. And then we can ask two things. We can say, what is the effective volume when we take this sort of flat surface and convolve it with a Gaussian? We can work out what that fuzzy volume is. We can then say, what is the volume of states that are within some distance delta of this flat surface? That's just the volume of a sphere with radius delta. And we can work that out and show that in the limit that t goes to infinity, the volume of states within a certain infidelity of our manifold is equal to the ratio of these two frame potentials, where this characteristic infidelity is a not too complicated function of t and the dimension of your Hilbert space and the dimension of your manifold. So this looks, maybe complicated. It involves a gamma function, but basically it goes like 1 over t with a constant factor that depends on the dimensionality. So the larger the dimension of your Hilbert space, the greater this sort of characteristic infidelity. And then the larger t, the smaller this characteristic infidelity. I won't go through the details, but basically there are a little bit more sophisticated arguments that one can go through where you're not making this sort of a flat Euclidean approximation. And the important thing that comes out of this analysis is that there's this notion of sort of a density of states at a given distance from your manifold. And so imagine we've got some arbitrary state psi in Hilbert space, And we say, well, what's the closest state in our manifold? And that has a certain infidelity, we'll call it I min. And then we say, what is the density of states, or the kind of distribution of states at a given, with a given minimum distance to the manifold? And that's what I'm calling eta here. And so in terms of that, we can now connect these two things. The exact measure of states within a given distance is just the cumulative distribution of this infidelity distribution. We can also relate the fuzzy volume, making a couple of weaker approximations. We can relate the fuzzy volumes in terms of the same distribution of infidelities, the distances to our realizable set. And then we can go further, and by integrating by parts, show that this fuzzy volume is actually related to the exact thing that we care about, this sort of cumulative distribution of states at a given distance. But it's not, what we would like to say, is that the fuzzy volume equals the set of states at some fixed distance from the set of states that we can make. But it's not that. It's actually sort of a weighted integral, where the weight depends on this density of states, which depends, sorry, I skipped a few things. It depends on the kernel function. And so that's going to, the blurring function will determine this kind of this weighting function, which will pick out different parts of this cumulative distribution. And so strictly speaking, this fuzzy volume is kind of a functional of the thing we care about, this really smoothed out version. But it turns out that all of these curves have very characteristic shapes depending on the dimensionality of the Hilbert space and the manifold. And that because of that, to a good approximation, that we can find for a given value of t for our frame potential, we can find some characteristic infidelity such that this fuzzy volume is roughly the volume of states within that given distance from the set of states that we could realize. Okay, that was a lot of math. The truth is that this relationship depends on lots of things. I won't go into details here, but I will just say that I worked out two paradigmatic cases. One is where your manifold is a real subspace of some dimension m, and the other paradigmatic case is where your manifold is a complex subspace of dimension m over 2. So here your parameters form sort of real and imaginary pairs in Hilbert space. And we can work out what this characteristic infidelity is as a function of the t parameter. And this is for when we're in a Hilbert space of dimension 50. On the left, we are looking at a complex subspace with various numbers of degrees of freedom. So these would correspond to increasing values of m, corresponds to increasing dimensions of our subspace. And we see, we get this behavior that we predicted from the simple analysis, that as t increases, this characteristic resolution goes roughly as 1 over t. And this the same is true whether we're looking at a complex or a real subspace. In fact, they have very similar behavior. They converge to the asymptotic result at large t, and they differ only a little bit for small values of t. So, all right, we're getting close to putting everything together. One thing I do want to note is that you need a very large value of t to say anything about your state space at small resolutions. So if you're talking about high accuracy, being able to approximate states to high accuracy, you're going to need a very large value of t. And just to, I want to kind of point out, almost all the works out there use t equals 2 to quantify expressiveness. And so if we plot, well, what does this characteristic resolution look like for small t values for various dimensions of Hilbert space? And as you can see, that the this characteristic infidelity becomes quite large rather rapidly. So you can have a circuit that has a very high measure of expressiveness when you're looking at t equals 2. But the characteristic infidelity might be something like 0.7 or 0.8. So basically, even though it would look like you've got a highly expressive circuit, what that really means is that you can only guarantee that you can make approximate states to an infidelity of 0.8 or 0.7, which is very poor. So the point being that t equals 2 is actually a very coarse measure of expressiveness. And I think this is something that people who work with this quantity would not be surprised at. But what this work shows is it allows us to quantify exactly how sensitive is t equals 2 versus t equals 4. Yeah, so this gives us a new way of understanding the limits of these frame potentials. Okay, so putting everything together, what I've shown is that the ratio of these frame potentials, these two kind of theoretical quantities related to T designs, you can actually think of as a volume, roughly, a volume of states that your circuit can approximate to some characteristic infidelity. And that infidelity, to good approximation, has this very simple form. It depends on the dimensionality of your Hilbert space D, the dimensionality of the manifold that your circuit carves out, which is M, and then some constant C that takes a small value. So this interpretation is exact as t goes to infinity. The looseness in it is that this characteristic resolution really does strictly depend on the shape and structure of the set that you're trying to characterize. And so it can be off by small factors. So with all these approximations, how well does this hold up? Does this interpretation, does it bear out? So I looked at a few test cases. So our first test case is, let's say we just pick an orthogonal set of states. So our parametric circuit is actually not parametric, but it's we're just looking at, we have a circuit that can make any computational basis state. And we look at the characteristic resolution, this kind of fuzzy volume compared to the true volume of states within a characteristic distance. And looking at dimension 10 and dimension 200, we find that this is actually an excellent approximation, and that this frame potential ratio really is telling us about a volume of states that are reachable. A slightly more interesting case is, let's say we have two qubits, each of dimension d. And again, we look at the probability, we compare the fuzzy volume to the true volume of states that are within a given infidelity of the states that we can make with these two qubits. And for small d, we find excellent agreement between the truth and this sort of heuristic fuzzy volume determined by these frame potentials. As we go to higher dimensionality, we do see a little bit of error, but it's not growing very rapidly. And that the error in the while the error in the fractional volume is quite large, the error in the resolution is actually not too big. It's on the order of 10–20%. So this is encouraging. Another test case that I looked at is what I call phase states, which are basically you have a uniform superposition, but each basis state has an arbitrary phase. And again, I looked at this for different dimensionality. And again, I find pretty good agreement as we go up to larger dimensions. In this case, however, as we get to larger dimension, you start to see this kind of heuristic fuzzy volume. The error in this characteristic infidelity is off by a factor of about 2. So it starts off very, very accurate, and it's off by a small factor as we go to large numbers of dimensions. But still, the bottom line is that this using this frame potential, interpreting as a fuzzy volume, is actually a pretty good proxy for the volume of states or the fraction of states that are within that we can approximate to a given infidelity using a parametric circuit. And just note about interpretation, given that the these curves are sort of very asymmetric, right? There's because they drop off so rapidly as a function of infidelity. If you were to say, interpret this curve as approximately 10 to the -4 of all states are within infidelity 0.5, then that wouldn't be very good, because there's a huge variation. There's a factor of roughly 100 in this volume of this fraction of states. But if we interpret the graph the other way and say, I have a certain fraction of states, 10 to the -4, and they are approximately within 0.5 infidelity of the set that our states that our circuit can make. We can make that sort of interpretation, because in that case, the error is only a few percent. Okay, so this is a useful interpretation, but you have to take it with a little grain of salt. Okay, so that's my proposition, is that using this frame potential ratio is actually a very useful way and meaningful way to measure expressiveness of quantum circuits. Now, one thing you might wonder is, well, how would I actually compute these frame potentials? So in practice, you can posit a distribution over your circuit parameters that'll induce a distribution on your quantum states. And if your circuit ansatz was simple enough, you might be able to actually work out by hand or analytically what these frame potential integrals are. You might be able to evaluate this numerically if the circuit doesn't involve too many qubits. But in general, you'll need to estimate this using some sort of Monte Carlo. And the way you would do this is you would pick a pair of random parameter vectors. Then you would figure out what states those circuits would produce. You compute the fidelity between those, you raise it to a power, and then you sort of average over that. So that's the naive approach. And that's okay if you have small dimension and small t values. But if the dimension or t gets, at all large, this is going to be very inefficient. And the reason is that in high dimension and for large t values, most states that you pick are going to have a not very high fidelity with each other. And then when you raise that to some large power, that's going to be close to zero. And so most states that you pick just blindly are going to contribute very little to your estimate of this frame potential. So what you really want to do is do some importance sampling. And there's a technique called annealed importance sampling, which is actually a perfect fit for this application, because what we want is the frame potential evaluated for multiple values of t. And annealed importance sampling actually does this. We can think of these t values as sort of inverse temperatures. And annealed importance sampling generates samples progressively at these different temperatures, going from the easy ones at low t value to the difficult distributions at high t value. And as you do this, you take the sequence of samples. You can use Metropolis Hastings to do a Markov chain to get from each distribution to the next. And then there are these factors that depend on the fidelities of your sampled states at the differences of the t values. And that ends up becoming the thing that you average to get your estimate of the frame potential at a given t value. And this turned out to be much, much more efficient than naive Monte Carlo when d and t become large. And so this is, makes this a somewhat practical way of doing this. Okay, in the last few minutes, I'm going to actually apply this to a few different circuit ansatz. Kind of as our baseline, these are what the plots look like for circuits that generate, say, all the states and within a complex subspace, or all the real states within a certain subspace. And looking at the complex subspace on the left, as the dimension goes from a small value 10 up to a value of 300, we get this sort of characteristic curve where at large dimensions, we find that nearly all the states can be approximated to our given distance, our particular distance from the subspace. So for example, interpreting this graph, what that means is that if you were to pick a random state in Hilbert space, then with very high probability, its distance to the subspace that your circuit can make is going to be 0.8. And so this is, as D becomes very large, almost all states are the same distance from the states that you can make. And so this is what I call typicality. And this holds both for complex subspaces and real subspaces, although the curves look a little bit different. Okay, so let's look at actually at a parametric quantum circuit. So one of the circuit classes that I looked at are called commutative quantum circuits, sometimes called IQP circuits. And they're a relatively simple ansatz, but they're interesting because they're hard to simulate classically. They're also promising for quantum machine learning. They make nice generative models. And the structure of this circuit is that you have n qubits in the uniform superposition, and then you apply controlled phase gates or ZZ gates involving various subsets of qubits. And it can be 1 qubit, it could be looking at 2 qubits, it could be 3 qubits or higher, any number of qubits. But these operations all commute with each other, and that's why they're called commutative quantum circuits. It turns out the easiest case to analyze is the case where you have all 2 to the n minus 1 possible gates in there. So every possible subset of your n qubits other than the empty subset. And we can actually work out what the expressiveness is for these maximal commutative circuits. And on the left, I show the exact distribution of states at a given distance from these set of phase states. And again, we see this phenomenon of typicality, whereas we increase the number of qubits, we get to a point where almost all states in Hilbert space are exactly the same distance away from the set of states that we can make. On the right is the same thing, but this is now using this fuzzy volume as computed from the frame potential ratio. And we can see that it's, you know, they don't agree perfectly. In particular, as we go to larger numbers of qubits, this characteristic resolution is a bit too high. It kind of converges to around 0.4, 0.5 instead of 0.2. But we see the same phenomena of typicality, the sort of concentration of states at a particular distance from the realizable set. I also worked out the case for commutative circuits that consist of all 1 and 2 qubit rotations. And what we find is that, as you might expect, since the number of parameters is much smaller than the dimension of Hilbert space, as we go to more and more qubits, we're able to reach a much progressively smaller and smaller fraction of Hilbert space. So as we go up to 8 qubits, we're already finding that, you know, most of the states are at a distance 0.8 from what we can reach. So again, this is sort of saying, you know, as you scale these circuits up to higher number of qubits, they're sort of less and less expressive. They're reaching a smaller and smaller fraction of the Hilbert space, but in a way that we can quantify exactly how much of state space we're able to reach. For comparison, these are the plots for if your circuit made a real subspace with the same dimensionality as these the set of states from these commutative quantum circuits. And those are shown with the dashed lines. And you can see it has sort of a similar behavior. So roughly speaking, these sort of 1 and 2 qubit commutative quantum circuits have about the same expressiveness as a real subspace with the same dimensionality. Okay. All right. Lastly, I looked at a hardware efficient ansatz. And so there's various notions of what this means, but for this study, the model was we have n qubits that start in the 0 state, and then we apply alternating rounds of 1 qubit rotations and entangling gates. And for this study, the entangling gates are controlled Z gates. And we alternate between, they're always nearest neighbor, but we sort of alternate between, sort of even to odd connections versus odd to even, so to speak. And then we repeat this some number of times. And so for this first study, we took all these single qubit rotations to just be Y rotations. And I plotted the expressiveness in sort of naive way, where I was taking the dimensionality of the subspace to be the number of parameters. And so initially it looked like, aha, as we increase the number of layers, these curves are moving to lower and lower infidelities. That means more and more of the states were able to approximate to small infidelity. So it looked like, oh, as we increase the depth of the circuit, it's getting more and more expressive. But it turns out this was misleading. And this points out something that you need to be careful of that I'll say a bit more on the next slide, which is that the number of parameters is actually not the dimensionality of the set of states that the circuit can make. If you go and compute the dimensionality of this manifold by looking at the quantum Fisher information matrix and taking its rank, what this shows is that actually, once you get past 2 or 3 layers, your expressiveness is really not increasing at all. That this ansatz kind of saturates at just a few layers, and you're really not able to explore that much of the state space. So then I looked at, well, let's suppose we replace these Y rotations with arbitrary 1 qubit unitaries. Does that increase the expressiveness? And it does a little bit, but again, not very much. We find that after a few layers, it sort of saturates and you really don't reach much more of the Hilbert space. And so kind of tentative results here are that this structure of circuit is actually not very expressive. It saturates at just a short depth, and a lot of the states in Hilbert space cannot be approximated to any decent accuracy. And again, this highlights the importance of correctly identifying the dimensionality of this set of states that you're trying to characterize. So that's a little bit of a catch-22, right? We're trying to understand the expressiveness of a circuit, but to do that accurately, we need to know its dimensionality. So work that I'm currently doing is to actually use this, take the behavior of this pairwise fidelity as a function of t, and from that to extract an estimate of the appropriate dimensionality. And once that's done, then you can map that to a characteristic approximation tolerance. Some other work that that is ongoing is, I showed that this volumetric interpretation holds reasonably well for several different types of parameterized quantum circuits, but I'm working on making that more rigorous. Seeing are there any cases where it's a really bad interpretation? Can we make this? Can we bound the sensitivity of this interpretation to the structure of the circuit? Like, are there circuits where the set of states you can make have some very, do they intersect, or are they very tightly curled, and does that mess it up? Or can we show that actually parametric quantum circuits tend to give you fairly nice looking manifolds? And the other work that's ongoing is I'm continuing to look at different ansatz. What I showed you is just kind of the start, but looking at different ansatz and really studying how does the expressiveness behave at different resolutions as a function of number of qubits and circuit depth. Okay, so in summary, I posited a formal but intuitive definition of circuit expressiveness, and then I presented a new interpretation of frame potentials in terms of a volume of states that you can approximate to a given accuracy. Then I that means that you can look at the expressiveness of parameterized quantum circuits in terms of the ratios of frame potentials at various values of t. And studies are ongoing. This is ongoing work. And some tentative observations is that we see this notion of concentration, where at higher dimensions, almost all states are approximated equally well or equally poorly. We find that commutative quantum circuits are about as expressive as real subspaces. And then we found that this hardware efficient ansatz, at least the version I looked at, is a fairly inexpressive circuit, and it saturates its expressiveness at fairly short depths. Okay, that concludes my talks. Thank you very much for your attention, and I'll take any questions you have.
Thank you, Ryan. Thank you for the nice talk. It was really interesting. I have many questions, but I'll open the floor first to other folks. Any questions from the audience?
Hi, actually, I had a question about the last ansatz you were looking at.
Yes.
Like, can you explain more why, or how you calculated m differently, and why it is that the rank of the Fisher matrix is lower than the dimension of the set of angles?
Yeah. So how I calculated it. So what the difference is, so these curves in the with the dashed line, that's using this very simple this kind of heuristic formula that I showed, where for a given if you know the dimension of your Hilbert space and the dimension of the manifold, then that tells you at what value of infidelity does this fuzzy volume equal the true volume. Okay, but that depends on the dimensionality of the manifold, which in principle you don't actually know. So naively, you just take that to be the number of parameters, the number of angles. But in a circuit, right, like this, it might be that these angles are not all independent, right? They actually sort of there are different combinations of them can move you in the same directions in Hilbert space, right? So you can look at the what's called the quantum Fisher information matrix, which is sort of like the Jacobian, but it actually properly accounts for the fact that global phase doesn't mean anything when you're looking in the Hilbert space. And so, but you can sort of think of it as the rank of this quantum Fisher information matrix is how many different directions do my parameters let me move in Hilbert space. And so you can calculate that from the Jacobian. So I just I picked some random theta values and took the derivatives and calculated the Jacobian, and then formed the Fisher information matrix, and then computed its rank. And I did this for a bunch of random angles, and it's pretty much always the same. And so what I found was that for one or two layers, the rank is equal to the number of parameters or close to it. But beyond that, it just really didn't increase very much. And so, that was a surprise to me, but it showed that, really once you get past a few layers, these additional rotations aren't really letting you explore any new parts of Hilbert space.
Wow, that's super interesting. Thanks for the clarification.
Yeah. I mean, it would be interesting to look at if we were to replace these CZ gates by C0 gates, or to maybe choose a different, different starting state, like instead of starting in 0, if we chose the plus wouldn't be different, but like the Y rotation, poly Y eigenstates or something. So there's a lot of different ways you could go, but yeah, this is just sort of the first thing I didn't actually. I was just doing this yesterday, right? So this is fresh, very fresh results. So I'm not fully understanding it myself, but that's what this is telling us.
So
you can also ask what happens if you go to more qubits, right? I would imagine that you could go a few more layers before it would saturate, but that would be something interesting to look at.
Yeah, thanks for sharing the hot off the press results here. Yeah, I think it's interesting. Actually, I'm curious to know, when I saw this, I immediately thought, what does this say about reachability deficits for things like QAOA? Because you're looking at very targeted states, right? For certain, let's say that you look at a max set problem, right? And you look at a very, very specific, you're looking at a very specific set of states. And people have already noted this before. I think from the Biamonte group, they had this nice paper on reachability deficits in QAOA. I'm curious to know, if there's anything here that can sort of tell us more about that and help us understand sort of how the design of the circuit is related to the approximation ratio or the reachability of that quantum circuit.
Yeah, that's a great question. I think it's not clear to me how you can. So, I started off by saying, well, for a given problem, you actually have a target class. It's not the whole Hilbert space, but it's some subset of states. The arguments that I used, I'm not sure that you can simply replace all of Hilbert space with some arbitrary target class. And I'm not sure everything would still the arguments would all follow through. So I don't know that you could do that. One thing you could sort of do is you could sort of look at the sort of reachable, volume of the target class. And then you could look at the, sort of this fraction that you can reach with your circuit. And if the latter is much smaller than the former, then that's sort of a bad sign. But even if they're the same, that wouldn't prove that your circuit can make the states you care about. So it's sort of getting at that. It's something you could do right away with this, but it maybe wouldn't quite answer the question that you're talking about, that you're interested in. The other issue is at Quawa, it's sort of right. The set of states you want to make at the end of the day, they're just computational basis states. So they don't need to be very expressive, but the trick is how to get there, right? So that's what Quawa does for you, is it sort of takes you on this detour through this complex Hilbert space to get you to a classical state. And it's that freedom to leave the classical state space and go outside of it that lets you, kind of do this optimization. And so, it's interesting, and I don't really understand it, but what does that state space need to look like? What's the state space that you need to be able to explore to get to the right classical state at the end?
Right. Yeah, and I mean, it's interesting to think about here if I guess how this, what the connection is. But yeah, thank you. I mean, I think it's some interesting stuff here. I would be interested to know how this is affected by noise. How does how does this affect your reachability once you add in things like noise, right? I mean, depending on the type of noise, I imagine that this distance will further shrink, right?
Yeah, that's an interesting question. I hadn't thought about that. I was looking at pure states, but so you could look at systematic errors which weren't absorbed by your variational parameters, but then if you had some sort of decoherence, that would further shrink your state space. And yeah, how would this extend to mixed states? I'm not sure. But yeah, that's a great question.
Okay. Well, thank you, Ryan, for your time. It's about 7 minutes over, so I want to respect your time and everybody else's. So thank you again. If you have questions, more questions for Ryan, please email him directly or email me, and I can forward you his information as well. So thank you again, Ryan, for the really nice talk.
Oh, thanks. My pleasure.